Hello everyone. So in this lecture we're going to move on to a new concept, and that's basically modeling a relatively complicated circuit by a simplified version of the same thing that would behave the same, and this is called Thevenin or Norton equivalent modeling. We're going to first ask the most important question of why are we interested in doing something like that. So as you've seen, gradually we started with relatively simple circuits with only a few components, and as we get closer and closer to doing real applications with our electronic components, the circuits are going to start becoming more complicated, meaning that you're going to have a lot more components that are involved in the operation of the circuit. So with increased number of component count, then when you want to use a specific part of the circuit and connect that to a different part or a different system with more components in the other system, sometimes it's a lot easier if you model each component or each sub-circuit or each subsystem of the circuit or the total system that you're dealing with into a simplified version, so that when you connect them to each other you can quickly analyze the whole system, or the combined versions of each component connected to each other would be easier to analyze. In other words, when you're dealing with a large application and you're designing for a large application, normally the best path to successfully do it is to break the large system into smaller subsystems, and then each subsystem is going to be designed based on a certain requirement, and then once each subsystem is already designed, then you connect these subsystems to each other, at which point when you're connecting them to each other, you don't necessarily care about all the details within the circuit, and rather you only care about what happens from the ports or terminals that are getting connected to the rest of the components. So in that sense, it's a really useful technique that we're about to discuss here, and that's how to take a complicated circuit and then shrink the complexity down to a minimum level and represent the same functionality with a much simpler circuit that would behave the same. So the good news is that you can take pretty much any electronic circuit and turn it into a source with a resistance or impedance that is either in series or in parallel to that source, depending on what kind of source you're about to choose. If you choose to represent the functionality of the circuit with a voltage source, then there would be a resistance in series with that source. And if you choose to represent the functionality of the same circuit with a current source, then there would be a resistance in parallel to that source. Now, each one of these two models, they're actually, you could be arbitrarily picked to represent your original circuit. In this specific lecture, we're going to start by trying to represent the circuit with this model, and then in the next lecture immediately after that, we're going to try to represent the same circuit, this time with that model. And these two could be arbitrarily picked based on a specific application that you have, where you're going to take this model and then connect it to the rest of the circuit. Sometimes it makes more sense to use a voltage source. It makes the analysis for the rest of the system easier if you use a voltage source. Sometimes it makes more sense if you use a current source. If you end up using a voltage source in series with a resistor, this model is called a Thevenin model. So with that, then this resistance is called R Thevenin, and Thevenin is a name, and this would be voltage Thevenin. And if you end up using the current source, this model is actually called a Norton model, and so then the resistance is called R Norton, and the current source, the value of the current is called the current Norton, or I Norton. And Thevenin is spelled like this, if I'm not mistaken, and Norton is spelled like this. Let me double check to make sure. So yes, and now, so what are we doing here? We're basically saying we take these two terminals for the circuit, we put a box around the circuit, and our claim is that I can represent the functionality or the current and voltages, the current voltage behavior of these two terminals with a circuit that looks either like this or that. And obviously, the motivation here is that instead of dealing with, in this specific case, 1, 2, 3, 4, 5 components, now I only need to be dealing with 2 components in each one of these 2 cases, which obviously reduces the complexity to a large extent. So, if that's the claim, let's see how we can actually accomplish that. Now, when I say this circuit is equivalent to that, in the domain of electrical, what we actually mean is that the voltage current characteristic of these 2 ports are going to be exactly the same. In other words, what I'm saying is that no matter what I connect to this, if I take the same thing that I connect to this circuit and put it right here, I would see the same voltage and current. Voltage across and current passing through that component. So let me repeat again. Equivalency means that in the domain of electrical, if I put a component here, no matter what that component is, the current that is passing through that component and the voltage across that component would be the same if I take the same component and put it here. And with that, now we're going to start seeing if we can actually represent that circuit with this model. So let's start with this hypothetical model that I'm basically claiming that would represent that circuit. If I leave this port open and basically measure the voltage, that's one of the situations that could happen and should be included in equivalency. In other words, I said if I put any component here, right? So any component, one of those any components would have been a very large resistance, or in other words, an open circuit. So if I leave this circuit open and I leave that other circuit open, the voltage that I measure for this one has to be equal to this one. So let's get to this simple one and see what would that be, the voltage. What would be the voltage in that case? So if this is open, doing the simple 3-step analysis, it's pretty much obvious what happens to this voltage. If I take that as, say, ground, I'm not going to do it, I'm just going to quickly explain that. There's no current passing through this resistor, so when I write the equation for this, if this is my ground, that would be my Thevenin, and the current passing is 0, so if I write the equation for this resistor, the equation would look like this. 0 is equal to Thevenin minus this voltage, I'm going to call it Vx at this point, divided by R Thevenin is equal to 0. So Thevenin minus Vx divided by R Thevenin is equal to 0, which immediately tells you that Thevenin and Vx are the same. So in other words, what I'm getting here is that if I leave this model, hypothetical model, open, then the open circuit is the same as Thevenin. And if I'm claiming that these 2 circuits are the same thing should happen here. In other words, when I want to model this circuit with this Thevenin equivalent, in order to figure out what Thevenin is, all I need to do is to leave this circuit open, calculate this voltage, and then that would give me the value for Thevenin. So let's do that and quickly calculate Thevenin. So we know now that V open circuit is the same as Thevenin. Now, When it gets to doing this, now I'm back to doing circuit analysis. You remember the promise was that everything here in this course and this courses after this is all about circuit analysis, and the algorithm is always the same. So you start by basically picking what your nodes are. So let's say this is one of my nodes. That's one of the nodes. Actually, this is one of the nodes, and that's another node. So there are 3 nodes in the circuit. Let's assume I'm assuming this is my ground. Immediately with that, the voltage, and let me actually check I don't have the voltage written here. So it's 25 volts. So this is 25. So that becomes 25 volts. That's the equation for that component. And then I'm going to call this one, say, V1. So now we have already labeled all these, and V open circuit is what I'm going to label that one. Now the currents, there's the current. I'm going to call that I1. Let's call that I1 again, because I can write KCL immediately there. And then I'm going to call this I2. Obviously this is 3 amp. And then obviously, because that's open, this current is equal to 0. So now I have all the currents labeled for the circuit as well. We start writing KCL, an equation for components. I don't have to write KCL for that node. I already wrote the KCL for that node, so the only KCL left is for this node. So KCL would give me this equation. And 3 amp is going in, I1 is going in, and 0 on the other end is going in. So 3 plus I1 is equal to I2. So I2 is equal to 3 plus I1. That takes care of the KCL equations. Now we write equations for components. So we have 1, 2, 3, 4, 5 components. The equation for that component is already given me 25 volt up there. The equation for this component has already given me 3 amp for this. So there's only 3 components left. I write the equation for that component. I1 is equal to 25 minus V1 divided by 5. I2 equation for this component is V1 minus 0 divided by 20. And equation for that component, it's easy. 0 is equal to V open circuit minus V1 divided by 4, which immediately gives me the result that says V open circuit is actually equal to V1. Whenever there is no current passing through a resistor, the voltages across the resistor would be the same. Just a simple result of the Ohm law. Okay, so with that, now I'm going to solve this set of equations. I take these two and put it in that. So V1 divided by 20 is equal to 3 plus 25 minus V1 divided by 5. I can multiply both sides by 20, so I get V1 here. So V1 is equal to 60 plus 100 minus 4V1, or in other words 5V1 is equal to 160, which gives you V1 being 160 divided by 5, and that gives you 32 volts for V1. Now as soon as you have V1, knowing that V open circuit is the same as V1, that gives you V open circuit is equal to 32 volts, which then gives you the Thevenin voltage is equal to the Thevenin voltage. So if we claim that these two circuits are equivalent to each other, the V Thevenin for the simplified model has to be equal to 32 volts. Now again, let's go through the reason for that, because once you know the reason, then it's most likely it's less likely for you to forget this, because this becomes intuitive. Once you know this is the model that you're picking, if you leave this the ports of this model open, the voltage that you see in the across the two terminals would be equal to V Thevenin. And since these two are equivalent to each other, the same thing has to happen for the large circuit, meaning that if you leave it open, you have to get the same voltage, or V Thevenin. So in order to calculate V Thevenin for this model, You just leave this open, calculate the voltage across the terminal, and that would be the Thevenin for your Thevenin model. Good. Now, let's move on to our Thevenin, which is the next step in the process. So, let's go back to this model and do something to see what the process to calculate our Thevenin for this circuit should be. So in this circuit, if I actually turn off all the sources, all the independent sources in this, which in this case would be just the Thevenin, and by turning a voltage source off, we take basically the voltage and make it 0, which means the voltage across these two nodes should be 0. Now, when voltage across two nodes is 0, that means that the two nodes are shorted to each other. So by turning off a voltage source, I am actually shorting out the two ends of any independent voltage source in the circuit. So if I do that and look back into these two terminals and try to calculate the equivalent resistance that I see from that box, it's kind of obvious that the circuit that I will be dealing with is this resistance and then short circuit, right? So it's resistance, nothing, and then comes back. So looking back, I'm just going to see our Thevenin as a result, right? So if I short this out, looking back to the circuit, I'm going to calculate our Thevenin. If I do the same thing to that circuit, since I'm claiming that these two circuits are the same thing has to be calculated for this circuit, meaning that now if I go inside this box and turn off all the independent sources in the circuit and then calculate the equivalent resistance looking back into the circuit, I should see our Thevenin. So the value that I calculate at that point is our Thevenin. So let's do that. Now at this point, I'm going to remove this Norton model, and like I told you, we're going to go back to the Norton model and calculate that for the same circuit in the next lecture. So for now, I'm going to remove it and redraw the circuit and remove or turn off all the independent sources. So we get here, and these are the resistors. They all stay, but then that voltage source becomes a short circuit. Now we have a current source here, and let's think about the current source and how we turn it off. When we turn off a current source, that means that the current of that current source has to become 0, meaning that there should not be any current going through by that path, which is equivalent to an open circuit. So you open up the current source and short out any voltage sources when you turn them off. So let's repeat. For any voltage source, when you turn it off, the voltage has to be 0, voltage across, which means you're shorting out the two ends of the voltage source. For any current source, which means that the current is going to go down to 0. In other words, you're opening it up. When you have an open circuit, there's no current passing. So this is a result of turning this circuit down here, is a result of turning off all the independent sources in your circuit. So this is my 4 ohm resistor up there. This is the 20 ohm resistor, and that's the 5 ohm resistor. Now, looking back into this box, I need to calculate the equivalent resistance here. So R equivalent, and R equivalent in this case is actually our Thevenin. So that said, it's quite simple to do this. There is this resistor in series with these two resistors in parallel that is equivalent to that. So that would be 4 ohm plus 20 in parallel with 5. So that would be 4 plus 100 divided by 25, which is 4 plus 4, and that's 8 ohm. So the equivalent resistance of this circuit at this point would be 8 ohm. Therefore, once we're done with this process, I have managed to represent that circuit up here with the circuit down here, which we call the equivalent, the Thevenin equivalent of that circuit, and the values for the Thevenin and our Thevenin are correspondingly 32 volts and 8 ohm. So from now on, whenever I want to take this circuit and connect it to anything else, I can actually take the equivalent of that circuit and connect it to anything else. Let's say I wanted to connect that to just the resistor. Now, to find out what would be the voltage across that resistor, or what would be the current that is passing through that resistor, it would be exactly the same as connecting it to this circuit and calculating the current and voltage. The difference is that if I connect it here, it's a very simple calculation to calculate the current and the voltage across the resistor, whereas if I connect it to that circuit, it takes quite a bit of work to actually calculate those values. So this is much simpler to do. I'm going to repeat the process one more time, stop and move on to the next lecture when we discuss the Norton equivalent. So the claim is that I can represent this circuit with this model. Therefore, whatever happens to this circuit has to happen to that circuit. That whatever could include when the case where I leave this circuit open. So if I leave this circuit open, the voltage across this would be V Thevenin. It's an easy calculation. So I do the same here, leave that open. The V open circuit is actually equal to V Thevenin. So I go back to my routine, calculate the V open circuit, doing exactly the same thing. And then once I have the V open circuit up here, and notice that I intentionally assume that's ground, at which point the voltage across this thing is the same thing as the voltage over there. V Thevenin is actually a voltage across, but once I assume this is ground, the voltage across would be the same as the voltage there, because voltage across is that voltage minus this voltage. That being 0 means the VOS is actually the voltage across. Calculate that. That would be my V Thevenin. Now, for the equivalent resistance, I go back to this model and say, if I turn this source off, the resistance that I see would have been R Thevenin. And the same thing has to be true for that circuit. So I turn off all the independent sources. Keep in mind, you only turn off the independent sources. If there are dependent sources, they have to be left out. They just stay there. So all the independent sources, you turn them off, which means you short out all the voltage sources and open up all the current sources, and then calculate the equivalent resistance. And looking back into this, this is the result of turning off the sources, and the equivalent resistance at that point would be 4 plus these two in parallel, and that would have been 8 ohm, and we are done with that. Thank you for your attention. We're going to move on to the next lecture where we discuss Norton equivalency.